So now we're going to solve a two-dimensional conduction problem. This one's a challenging problem. Let's just jump into it. We have a two-dimensional straight triangular fin of length 50 millimeters and base thickness of 20 millimeters. This is the shape. It's triangular. The thermal conductivity is given. The temperature of the base is all 50 degrees C is given. Exposed, well, this is the whole base right here. It's exposed to the fluid at this temperature and that convection coefficient using a finite difference mesh with delta X equal to 10 millimeter. So if you're going 50 millimeter, you would put 1, 2, 3, 4, 5, 6 columns, and each space right here would be 10 millimeter. And then if you do the same here, you find that delta Y is 2. So if this is half of this is 10 millimeter, then you have 1, 2, 3, 4, 5, 6 nodes, 5 divisions, hence 2 millimeter for the delta Y. Okay, so taking advantage of symmetry, determine the fin efficiency. Well, to calculate the fin efficiency, it's how much heat is transferred into the fluid off of the fin divided by how much would be transferred maximally as if every bit of the fin was at the base temperature. That's our basic equation for fin efficiency. So you would say, well, if I calculated each of these temperatures, node 6 and node whatever that is, 11, then node 15, etc., what I could do is I could get an average temperature here. So the Q actual would be the convection coefficient, my area, some temperature surface average along that edge minus the temperature fluid. Okay, how about the maximum? HA, guess what? This average surface temperature, if I have infinitely high thermal conductivity, then everywhere on the surface of the fin is the base temperature, TB minus T infinity. So you say, look, I can calculate it getting rid of those same areas, same H's. It's really this average surface temperature along here versus the base temperature. So it boils down to, if I want to calculate this fin efficiency numerically, I need the surface average temperature. Well, can you see that let me clean this up a little bit. For this node 11 and that node 15, they have more weight or length for that edge than maybe node 6 or node 21. So what we do is we think about cut it in half. This area is associated with node 6. Cut it in half. This area is associated with node 11. Maybe change color. This area is node 11. Change color again. This is the area associated with 15, and then this is the length with the area associated with 18, etc. So if I said the average temperature, it would be numerically get the temperature at node 6. Then get the temperature at node 11. Then get the temperature at node 15, 18, 20, and 21. But I want to average them. But this first one is only half the weight of the other ones. And then I look and I say, okay, it's like 1, 2, 3, 4, 4.5, 5. Divide the whole thing by 5. And there it is. There's your surface average temperature. Put that into this equation right here. Subtract off the fluid temperature. The fluid temperature is a given of, 20 degrees C. Down here, put in a base temperature of 50. Subtract off 20 degrees C, and there is a numerical estimate of your fin efficiency, my triangular fin efficiency.
Accurate is that?
Very. Yeah. Now, if you want to go in and you want to discretize with the higher number of nodes, don't just stop at 21. Maybe put up 200, 2,000. You'll get better agreement with somebody else's more detailed analytic calculation of it. But that's how you do it. So numerically, what does it boil down to? Have to get those temperatures. Once you get them, you can infer a fin efficiency. Okay. So what we do is we bust up in a mesh. And let me do this. I look, and I like to put in intermediate blue lines, sort of subdividing both vertically as well as horizontally. Do you see my lines don't go through the node, but between the nodes? And that way I can see an area or a volume, it's an area in 2D, for this node right here. That I just shaded as node 8. See that? And then I look and I say, you know, node 8 and node 9 are neighbors. They share this fence. What is that quote? Good, strong fences make good neighbors. There you go. They have a fence there. This one between node 8 and 7. This one between 2 and 8. And this one between... Is node 14 a neighbor, a near neighbor of 8? No, there's no conduction path between them. All right, so only conduction path for energy balance will be node 8, 9, 8, 7, 8, 2, 8, 13. Those are the participants. Okay, so what we do is we then can write it. Let's do it not for node 11. That's a harder one because we have convection off of this edge. But let's do it for node 8. What does it look like? It looks like this. Go in a couple steps. Say, I'm going to have conduction from node 2 into node 8. Then I'm going to have conduction from node 7 into 8. And then conduction from node 9 into 8. And then from 13 into 8. I like to write them. I recommend you write them. The energy balance equation as if 8 is the cold neighbor of everybody else. And just write it that way. Believe me, the signs work themselves out. Got it? So you say to yourself, it's got to be some thermal conductivity, some area divided by some length times the temperature 2 minus temperature 8. Likewise, thermal conductivity, area over length, temperature 2 minus temperature, not 2, 7 minus 8. Plus thermal conductivity, some area length, temperature 9 minus temperature 8, plus thermal conductivity, area to length, temperature 13 minus temperature 8. If that truly is balanced, if that equation is balanced, I have the final calculated temperatures, it sums to 0. All the inflow is equal to the outflow. It's steady state conduction. All right, what are these hard parts? It's what is this area and length for the connection between 2 and 8? What is this area and this length for the connection between 7 and 8? Likewise, this area and that length. Those are the hard parts. So you tell me. You rewrite these in terms of the area will be something like, oh, I think it's delta x times delta z. Oh, I think the length is delta y. No, I think the length is delta x for this one, and the area is delta x times delta y. No, it's delta y times delta z. I'm giving you the options there, right? All right, so should we do these clicker style? Okay, do you know of any other options for the area? This would be answer A, answer B, or answer C. And which one do you want to do it for? Do you want to do it for this one first of all? For the node 2 to 8, what is the appropriate area? There's your 3 choices. You could talk with your neighbor. All right, let's go ahead and stop. All right, okay. So the area is the height times the depth because you're going from node 2 to 8. Node 2 to 8, it's this height times the depth. Depth is delta z. So what is the height? Either delta y or delta x. Delta y, let's grade it. What am I missing? 26 of us? No, come on. Yes, sir. What am I missing? Why do I got 26 incorrect? 62% of the class picked C. I mean, isn't that the correct answer? All right. Okay. Well, I thought I was a very successful educator. You just put me in my place. A and B. You have only a 50-50 guessing game here. For this problem, from 2 to 8, what is the separation distance that the conduction needs to flow through? The L. A over L. What does L represent? I'm going from this node to that node. Let's start the clicker. Go ahead and input your response, please. And we'll show the results. Okay, so from 2 to it's really a conduction. This is the length right there that we're interested in between the two temperatures, and that length is delta X. Delta X. So hey, we're getting better. Now we just switch this around. Do you want to handle 7 and 8 or 9 and 8? Let's do 9 and 8. All right. So for this area right here, for this term, 9 and 8, is the correct area for the flow of heat across some perpendicular area. Is that area delta Y times delta Z? Answer A. Delta X times delta Z? Answer B. Or delta X times delta Y? Answer C. So that area is represented by this length of the line times the depth. So that length of that line is dx. So the result is dx times dz. B is the correct answer. Very good. We're improving. The last one, what is the length in this equation for node 9 to 8? Is it A or B? Let's go. When are we going to get 100% correct? I can't fit this on here. They won't let me resize this box either. Oh, no, they will. Good, they improved the system. So for going between 9 and 8, it's the length is the distance dy, which is answer A. Very good. It's still too large of a box. I need to get that smaller. Okay, it won't let me do that. Fine, go away. All right, so you have to struggle. The hard part isn't the K and it isn't the delta T's, it's the area to length ratios for each of those. And then you write it for node 11. Now, if you write it for node 11, is there any way that there could be a conduction path from 6 to 11? A lot of students want to make a conduction path, but there isn't. If you look at this line and this line, they join right there. There's no shared area between 6 and 11. There's a shared area between 5 and 11, and 10 and 11, and the convection and 11. And those are the only three things that are in our energy balance for node 11. So if you could look, you can kind of see this is the final energy balance for the node 11, or this maybe is a better way of writing it. Okay, you have to write energy balances for each of those nodes. Then you have to figure out, okay, I've got a bunch of nodes, 11 of them, or no, 21 of them. Some of them I know, this is to set the base temperature. All of these, the first 6 have the same base temperature, which for this problem was what, 50 degrees C? And the rest of these I have to calculate. So that's the challenge. How long do we have? 20 minutes. I'm going to try my best that I can in Excel. Good luck, right? I mean, it's kind of a long problem, but I'll try it, okay? So let's jump to Excel. Go new. I'm going to close out my clicker to save some room. Ending the session. Saying goodbye to that. Moving this over here. All right. There's a couple different strategies for using it. If you look at a video that I produced last time I taught this course, I solved this problem with a full-blown matrix, 21 by 21. It's about the limit of Excel. You then try and invert it. It filled the whole screen. I put a lot of students to sleep. But we're not going to do that this time. What we're going to do is I'm going to set it up as if it's the mesh that you might see. So what we had a node 1, then, I'm sorry, let's start down here. This was node 1, then 2, then 3, then 4, then 5, then 6. Okay, and then we came down here and we had node 7, then 8, then 9, then whatever, 10, then 11. Okay, and then we came down here, we had node 12, 13. Do you see the pattern there? I'm not going to go all the way out to 21. But what I want to do is I want to put in my temperature for node 6 and then temperature. So I'll just say, okay, 50 and 50. Those are fixed temperatures, 50, 50, 50, 50. And I'm not going to change them. But I'm going to be looking to calculate and put into these cells numeric values that represent the final steady state temperature. Last time I didn't do it this way. This time I'm doing it a completely different way. So I want to solve for those, and so I kind of set it up geometrically. And what I want to do is I want to get in copy this, paste it right there. And what I want to do is I want to set an energy balance for only those nodes that I don't know the value of. So I'm going to write an energy balance for this node 11 right up here, and it's going to depend on the temperatures that are above. This will be the temperature. Maybe I guess it to start at 40. Maybe this one I guess to 34. Maybe this one 36. I don't know. I'm just guessing some numbers, okay? 40, 50, whatever. So let me kind of populate this. Sorry if it takes me some time. All right, I need to just keep on populating. Hey, I got some crazy numbers. Get rid of that one. That was garbage. Oh, 45. I didn't say they had to be good. I just said they had to be in there. So if I came in here, I said, this is my energy balance equation. I would have to put the K times A over L times blah, 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 blah. So over here, what I'm going to do is I'm going to use something that Excel, some students showed me. It's called naming. I'm going to name some things. So let's say I'm going to call it dx. That's my spacing distance. Now, if you just put dx, it may think you're looking for a column dx, so put dx underscore, and then it's a variable name, all right? And so what is the value for my spacing dx? Do you remember what I had? 2 millimeter? 10, so 0.010 meters. True or false? False? Did I type that wrong? No, that's right. Okay, so let's do this. If you want to name it, you come over to this box. So instead of saying J2, I'm going to say dx underscore. And guess what? I just named it. That's its name. So now down here in equation, when I want dx, I don't go and say J2. I say dx underscore, and it says, okay, I like you, fine. Let's go do this one, dy underscore. Why do I put the underscore? Because it thinks it may be wanting column dy. Okay, fine. All right, what was this one? 2 millimeters. All right, now we can put in our conductivity. What was our conductivity? 50? No, 25. I'm not going to put in the units. I'd typically put in units. Convection coefficient. What was the convection coefficient? That was 50. Okay. Base temperature, TB. Probably if I'm going to do that, TB underscore. T infinity. That's not infinity. TINF. All right. T infinity was 20. And base was 50. Okay. And now I go ahead and that one's not defined, so let me just define it. dy underscore. There you go. How about this one? Define it by coming up here, COND. Define it by coming up here and putting CONV. Maybe I should hit return. You can pull this down and see which ones. It didn't take on the COND. I didn't hit return, did I? COND, hit return. Now when I pull down, it's a named parameter. Okay, let's do T infinity. TINF, hit return, and I pull down, it's up there. Did I leave off any that I need? DZ is 1. I'm going to just always put it in 1 so I don't have too much headache. So this is my energy balance equation for node 11. It's equal to, now I have my area for between 11 and the neighbor, which was 5, which is, here, let's do this, COND tab, or times, times delta y divided by delta x times this temperature minus that temperature, close parent. My L was divided by dx. dx is my L.
I'm saying when you get to the...
Oh yeah, I'll do that. I'll get to the convection. Right. All right, so then we have COND times, then we have dx divided by dy times, coming from the one below, minus that that's the delta T for the second conduction in from the bottom. And now I need the dl, thank you. But I'm going to put convection coefficient times my dl. I'm just going to put this one right there. I'll put it in there later. Times the dz is 1, so then it'll be a T infinity. I can put TINF minus that right there, close parent, and then hit return. That's not equal to 0. First of all, I need to put in dl. True? I think I need to put dl underscore. All right, so what is my dl underscore? Isn't it the square root of dx squared plus dy squared, close parent? Yeah, to close parent. Doesn't that give me my dl? Oh, yeah, now it actually, did it update? Oh, this is, you know what I'm going to do? I'm going to go back here and I'm going to define that as dl underscore. And then I'm going to see, nope, right there, dl underscore, done. Okay, so it's a little cleaner. If I want to take a look, it makes equations readable. All right? If you really wanted to, you could come in here and redefine each cell and call that cell T11. But be careful, it thinks maybe whatever. It may want to go out to column T down row 11. All right, guess what you would do? You would implement that formula for the next one. The next one's a lot easier. I don't have convection. Okay, let me jump back to my spreadsheet. When you do an interior, let's say I do it for node 10. That's our next one. It's 4, 11, 9, and 15 that are around it. And so it'll be temperature 4 minus temperature 11 or 10, sorry, times K times my area, which would be delta Y divided by delta X. That's this one. And then from 9 to 11, you pick up K times delta X delta Y. And then from 11 to 10, did I put 10 there? All right. It'll be the K times delta X divided by delta Y, and then K times delta Y divided by delta X times T15 minus T11 equal to 0 when it's in equilibrium. Well, guess what? The K's cancel, don't they? And then I can shorten this up, and so I'll have T4 plus T15 times delta y divided by delta x. You don't have to rewrite it like this. Minus 2 T11s plus delta x over delta y times T9 plus this is 10. T11 minus 2 T10s. That's equal to 0. You can rewrite it and package it a little different. Let's go back to the Excel and implement this one. Yeah. So let's do this one. This is equal to, for the two nodes over there, it was delta y divided by delta x times, and then we had this temperature plus that temperature minus 2 times that temperature, close paren, plus dx divided by dy times, in parentheses, this temperature plus that temperature minus 2 times the middle temperature, close paren. Did it look okay? Now, one of the beauties of this is I can drag this formula, not there, that's an edge, but I can do it to another interior node, to that interior node, to that interior node, to that interior node. So basically this formula, if I look at that node, see it's working with the ones around it. You're supposed to be impressed. Don't worry. So this one like this. But these right here, this one, this one, this one, this one, and like this one, I'll have to modify. But this one right here, if I just take and copy that cell and paste it right there, isn't that the right equation for the convection? And then escape. Probably some of you were sitting there, why doesn't he do that? You probably saw that before me. Do paste. Oh, come on now. Do a copy. Do a paste. I don't know what's all this control crap, paste options. I don't want to get rid of that. That never helps me. Never helps me. So I've got to work on this one right here. I'm going to do a copy and paste because it's probably just a modification of that formula. I said copy, please, and paste, please. Thank you very much. So if I look at that, yeah, see, I don't have anything below. So what is it? G9 and all this down here is gone. And when I look at the conduction from this one over, isn't it half of dx or half of dy? And then for the convection, isn't it half of dl?
You might want to put that as 2dx, otherwise it'll flip the dx and put it on top.
No, it won't. It's perfect. I think it's perfect. I do that all the time. So now, what I need to do is I need to write the balance equation for these on the bottom. And so this one is painful, is equal to, I had my conduction coefficient times my delta y divided by 2 divided by delta x times my temperature difference, this one minus this one, and parenthesis. All right. Plus, then we had, I'm getting tired of writing all this. Are you getting tired of looking at it? Dy. You want more? They want your coffee. I heard him. He needs to stay awake. Divided by y, 2 divided by dx times, and then this one minus that one. I'm missing something? Yeah, underscore. Thank you very much. And then I need the conduction from above, which is COND times dx divided by dx underscore divided by dy underscore times this one minus that one, close paren. All right, I may actually get far enough to show you something useful. That formula percolates, that formula percolates, that formula percolates. So really, what up here is I have temperatures. What do I have down here? I have E balances, energy balances for each node. Guess what? I need this one to be 0, that to be 0, that to be 0, and at the right place, they'll all be 0. So what I'm going to do is I'm going to do this. I'm going to say I'm going to do a dot product. Oops. Sum product. Okay, this is a routine where you have an array. This looks funny when you first see it. And you sum product it with another array. It's really a dot product. And then I'll do that for all of these. And if I sum that, backspace, equals sum of all of these. If I can just drive that to 0, I will have a solution. So I try my trick of coming up to data over to solver, and I say, yeah, I'm in this cell I-17. I want to minimize it by changing this variable and that variable and all these variables. So what I'll do is I'll just drag this, hit a comma, drag all that, hit a comma, drag all that, hit a comma, drag all that, hit a comma, and hit that. So it put all those variables in my list for changing those variables. And then what do you do with your two fingers? You cross them and you hit solve. And it comes back with a solution. Where did it go? Did I jump ship on that? Data, solver, all of this. Hit solve. Okay, why does it go here? Get rid of this. It tried to get it to 0, but it's a really poor 0. Or this is just not the right. Let me do this. I have a couple Excel spreadsheets open. I want to get rid of that one. That one already solved the problem, but I'm not going to show you that. I'm mean. Minimum, yeah, drive it to minimum, save to 0. Okay, well, it's trying, it's not getting well. So guess what we do?
Give up.
No. You have a different strategy completely. I'm going to do this. I'm going to move this down here for a second. There's a rhyme and a reason for that. And I forget about my energy balances, or I... How many minutes do I have? All right, I'll show you the solution here. Bear with me. The cell sheet that I just closed had it. All right, or just do this. This is not as accurate. If I do open and I do this one. All right. Okay, well, this is converged in the temperatures. The tip temperature is 39.09. Okay, how did we get it? Well, first of all, let me show you that this did not get the tip temperature to 39.09. So even though it tried this with solver, sometimes solver just doesn't work. Okay, this one is a linear problem and it's not a good solution. But if I come back to this problem, how did I get this one to converge? Long story is I use the energy balance and rewrite it so that it's like this. I don't have time. But I do iteration, and Excel is good at iterating. Anybody use Excel to iterate? All right, who wants me to finish the explanation of this next time? I will finish the explanation next time. Look up iteration in Excel. This works. Thank you for your attention. We have a quiz. All right, last time we were solving this triangular problem, were we not? We were solving for the steady state temperature distribution. And so the way I broke it was I put this triangle up in here. The lower part of that rectangle that I shaded has the temperature values, and then based on those temperature values, I have an energy balance. And what I wanted to do is I wanted to drive every one of these energy balances, which are based on the temperatures above, I wanted to drive that to 0. And so it's like a whole bunch of equations. I want to drive it to 0. And so what I did was I said, this is just using the sum dot product. It's a built-in function. It's kind of overkill for this first row, but maybe not for that row. It takes every one of these values, multiplies it by itself, and sums it up. Sum product. It's like a dot product. Okay, you can always look for what is this function doing if you just come up here and hit that, and then they have a little more explanation if you're new to Excel. So let's get rid of that. And then what we did was we summed them up over here, and I think I multiplied by 1,000. So Excel sometimes thinks a small number is close to 0. In engineering, we really want to drive it to 0, so we multiply by 1,000, tell it to do it again. It'll actually drive it closer to 0 then. But when I used a function that was in the data, and then under solver, it really didn't help, did it? So what I wanted to do was set up the problem a different way, and it was using iteration. So I copied over to a new cell. And so we have the same setup. We have our temperatures, and then we have the energy balances below, so we can check that later. But I needed to set up a different array of temperatures. And if you can see already in this blue, that doesn't look so good, does it? Excel doesn't like that. Basically, it's like the temperatures are referring back in an infinite loop. And Excel doesn't like that. So if I took a look at this value right here, what I did was I took the energy balance equation and I took out the value of the temperature in this cell. I forget what node that would be, maybe node 7 or node 8. I forget the numbering scheme. I think this was node 1, 2, 3, 4, 5, 6, 7. Okay, so I took that out of the energy balance and then used the other values of temperature to be able to calculate for T7. Maybe I should jump to a clean sheet and explain that. Insert new page. So our energy balances, maybe for that energy balance for node 7. And I kind of look, there's node 1, there's node 7, there's node 8, and I don't know what that node would be. 11? No, I can't remember. Another node. And you would do your little energy balance, and you say, okay, well, we have a K and A over L, and then we have the T1 minus T7. And then we have a conduction K, A over L, and then T8 minus T7. And we have a K, A over L times T11 minus T7. And when all that conductive flow into the node is balanced, that's when we have our final temperatures. Well, I want to rewrite this equation as T7 is equal to, then I'll have Ka over L T1 plus Ka over L T8 plus Ka over L T11 divided by Ka over L. I should probably put this associated with node 1, that's associated with node 8, that's associated with node 11. This is associated with node 1, A over L associated with node 8, and Ka over L associated with node 11. You see how this equation is being rewritten in terms of T7 is equal to the rest? And in it, I have the neighboring nodes. So that's what we implemented in Excel. And so what you can do is given the values of the temperatures right here of the neighboring nodes, you can get an update or new value of the temperature at that node in the middle. Same thing here. Using these 4 around it, you get a new value. And over here, same thing. Same thing. Now what? What I'd like to do is I'd like to do that again and again and again, iterate. So it's a little bit of cheating, but this value right here, I copy from below. So when you do that, so what I would normally do is I would put in, if I started this process, that's why I copied over here. I'm going to copy it. I would put in the values of my first guess. And I think I left off that last one. Let me just copy it too. Copy, come back. It's a little awkward to start this. Whoops, what did I just do? Control Z, stop all that. Careful, yeah, I need to be more careful. Let me try this again. Copy this group of numbers, copy. How did I miss the last row again? I had it selected. Did I not? Control C, Control. Now I got an extra one. You guys are really. Control C, copy. Now, put it there. Do a Control V, paste. Now I've got it. So these are just hard numbers. They're just whatever I put in there. Maybe I put in, I don't know, 46 as initial guess. Maybe I put in 23 as initial guess. It doesn't have to be great. I just have to put in some initial guesses. Based on these numbers up here, I can get a better number down here because these use the formula. But now I want to make it go again and again and again in a loop. Even just come right here and say, just replace that cell by this value. Now, if I hit enter, I want to drag that cell down. And there it's not liking because it's going in a loop. I'll fix that in a minute. Then I can grab this, go all the way across, and it really is complaining. You've got a lot of infinite loops and you're iterating. But at this point, you could tell Excel, I know what I'm doing. I'm going in an infinite loop. I want you to iterate a number of times. So you go under File, and you go under Options. Maybe a few of you have done this before. And you go under Formulas. And right here, it says Enable Iterative Calculations. Right now, it's not enabled. We want to enable it. And for this type of problem, put it at, I don't know, 1,000. Let it go 1,000 times. It'll go in 1,000 times. Hit OK. I mean, there's other things you can look at and read, but let's just hit OK. And now it's done that 1,000 times. And you've converged down to 39.0, down here, 39.08. And then you could come down and take a look. Does my energy balance equation look good? Well, it looks pretty good on a lot of nodes. But I'd even like that number to be smaller. So what we can do is go back and actually all I have to do is hit somewhere, put a number, and just it'll do another 1,000. Just sort of because I already started. If I want to go back and start it at my original value, I have to copy that matrix up and do it again. And then let's take a look. It did another 1,000. It's even closer, isn't it? Isn't that sum all driven pretty close to 0? And if you wanted to, you could do it again and, I don't know, put another value in, I don't know, 2. I'm just activating. And now it's driven it down to 10 to the minus 7. I mean, I don't need to do any more iteration. I'm there, okay? Or the numeric solution's there. So you take a look and it's, oh yeah, these haven't been changing, have they, to 4 significant digits. There's your converged solution. Out of your numerical methods class, this is called not Jacobi, but Gauss-Seidel. You can look it up, Gauss-Seidel. It's iteration.
So the numbers you just put in, you're just making a change to the sheet, it just makes another, just does it again.
So again, go under File, go under Options, go under Formula. It's a long way to get there, but you want to enable that iterative calculation. And if you only set this to 10, you could watch it slowly grind through. Having done this before, I know to set it to about 1,000 or more, maybe 10,000. I mean, you saw how fast it did 1,000 iterations. I didn't have to wait for it. So it goes pretty fast. And that's it. So we can cancel. I mean, let's do this. Do 10,000. Hit OK or hit return. OK, and then what we do is I'm going to try this one more time. Control C. Oh, good, I got it. Come up here. Control V. So now I can do this for the whole thing. Just hit equal to this one. Enter. And then just copy this whole thing. So what I'm doing is I'm bringing even those zeros there. So you can see what it did. How many iterations did I do? 10,000? So it converges pretty good in 10,000. That's how it's done. And I can scroll down and take a look. Okay. I find it's a little awkward to get this thing started in Excel. All right. Done with that. So we'll stop this recording right now.